Somewhere out past the orbit of Jupiter right now, a piece of another solar system is drifting back into the darkness it came from, carrying chemistry inside it that may have been sealed away since before our own sun ever ignited. For a few months in the second half of 2025, this object became the single most intensely studied visitor our solar system has ever received from beyond it, examined by nearly every major telescope humanity. Currently is pointed at the sky, from ground-based observatories to space-based instruments hundreds of thousands of miles from Earth. What those instruments found did not just add one more entry to a short list of confirmed interstellar objects. It rewrote what scientists thought they understood about how old, how active, and how chemically strange a wanderer from another star system could actually turn out to be. And it did so using nothing more exotic than sunlight, bouncing off a small, dark, ancient chunk of ice as it briefly passed close enough for our instruments to finally take notice. To understand why this particular discovery mattered so much, it helps to start with what makes an object interstellar in the first place. Nearly everything orbiting our sun, every planet, moon, asteroid, and comet, is gravitationally bound to it, tracing out a path that loops back around again and again indefinitely. Every so often, though, something arrives that does not belong to that system at all. An object that formed around a completely different star got flung out of its home system by some ancient gravitational disturbance and has been drifting alone through the empty space between stars ever since. When one of these wanderers happens to pass close enough to our sun for its gravity to bend the object's path just slightly before it continues on its way, astronomers get a rare, narrow window to study material that formed somewhere else, in the galaxy entirely. In all of recorded human history, only 3 such objects have ever been confirmed. The first arrived in 2017, a small, oddly elongated object that tumbled through our solar system quickly and quietly, showing almost no visible gas or dust streaming off it the way a typical comet would. That lack of activity made it maddeningly difficult to study in detail, and by the time telescopes fully grasped what they were looking at, it was already too faint and too far away to learn. Much more. Parts of its behavior remain debated among scientists to this day, simply because there was never enough time or data to settle every question before it slipped out of view for good. The second interstellar visitor showed up in 2019, and it behaved far more like the comet's astronomers already knew well from our own solar system, complete with a visible glowing coma and a clear tail. Because it was considerably more active, researchers managed to gather a richer set of chemical data from it than they had from the first visitor. Even so, both of these earlier encounters left the scientific community wanting more, hungry for a third opportunity involving an object bright enough, active enough, and detected early enough for the world's best instruments to get a truly thorough look before it disappeared again. That third opportunity arrived on July 1st, 2025, when telescopes at a survey station in Rio Hurtado, Chile, part of a network called the Asteroid Terrestrial Impact Last Alert System, built specifically to scan the sky every clear night, hunting for objects that might threaten Earth, flagged a faint, fast-moving point of light. Astronomers quickly traced its path and found their answer within days. This object was moving far too quickly to ever be captured by the sun's gravity. It was going to swing through our solar system once and keep going, never to return. It became the third confirmed interstellar object in recorded history, formally named 3IATLAS, with the number marking its place in that short sequence and the name honoring the survey system that first caught sight of it. What set this new visitor apart became clear almost immediately. Its path around the sun was more sharply bent, more extremely hyperbolic, than either of the 2 interstellar objects that had come before it. The shape of an orbit reveals how tightly or loosely an object is bound to the sun's gravity, and 3IATLAS traced out the single most extreme trajectory ever measured for any object of its kind, moving at well over 200,000 kilometers an hour when first discovered, and accelerating further as it fell inward toward the sun. Based on how fast the object was traveling, relative to the average motion of stars in our region of the galaxy, researchers were able to roughly estimate how long it had been drifting through interstellar space since it was originally ejected from whatever star system first produced it. That estimate placed its age somewhere between 3 billion and 11 billion years. Our own sun and solar system, for comparison, are roughly 4.5 billion years old. That range means it is entirely plausible this comet is older than the sun itself, having potentially formed around a star that lived and died long before our own star ever came into existence, then spent that unimaginable stretch of time drifting alone through the galaxy completely untouched, until it happened to cross paths with our solar system at all. Unlike the quiet, largely inactive first interstellar visitor, from 2017, 3IATLAS turned out to be a genuinely active comet. As it approached the sun, frozen material locked inside it began converting directly into gas, streaming outward to form a glowing coma and a faint tail. That activity mattered enormously to scientists, because an active object effectively releases its internal chemistry into space where telescopes can directly detect and analyze it, whereas a quiet, inactive body gives up almost nothing. The fact that the ATLAS survey system caught this object early, months before its closest approach to the Sun, gave researchers something neither of the two previous interstellar visitors had ever offered: real advance notice, enough lead time to schedule observing sessions on some of the most in-demand telescopes on Earth and in orbit. Well, ahead of time, rather than scrambling at the last minute once the object was already fading. Once the object's interstellar origin and extreme trajectory were confirmed, observatories around the world, along with space telescopes orbiting far above Earth's atmosphere, began lining up in sequence to take their turn studying it, coordinating schedules across multiple continents and multiple space agencies in the process. Chief among them was the James Webb Space Telescope, humanity's most powerful space observatory, an instrument tuned to detect infrared light rather than the visible light our eyes perceive, allowing it to pick up heat signatures and chemical fingerprints completely invisible to ordinary telescopes. Webb was never specifically designed with fast-moving, small solar system objects in mind, and tracking something moving as quickly as 3IATLAS pushed its tracking systems well outside their typical operating conditions. Despite that challenge, engineers successfully locked Webb onto the comet in August of 2025, capturing its first detailed spectrum, essentially a chemical fingerprint written in light. Webb then observed the comet again in mid-December of 2025, after it had already swung around the Sun and begun heading back out, this time using a different instrument tuned to mid-infrared wavelengths, producing the most detailed chemical readout ever captured from an interstellar object. What came back from those December observations surprised a great many scientists studying the data. The comet's chemistry proved unusual compared to typical comets that formed within our own solar system, showing an unusually high ratio of carbon dioxide to water vapor, breaking the pattern astronomers had come to expect after decades of studying homegrown comets up close. Then came an even more striking discovery buried in that same mid-infrared data, a clear signature of methane gas, streaming from the comet, marking the very first time methane had ever been directly detected coming from an interstellar object. Alongside that methane and carbon dioxide, Webb also picked up water vapor being released, along with something genuinely unexpected: a distinct atomic signature belonging to nickel. Finding a metal like nickel escaping from a comet is unusual, and it offers researchers a clue about the raw ingredients mixed into this object when it first formed, likely billions of years ago, around a star system entirely different from our own. Methane's presence mattered more than it might first appear, precisely because methane is such a fragile, lightweight molecule, one of the simplest hydrocarbons that exists. Exposed to raw cosmic radiation over billions of years, the exact kind of constant bombardment an object drifting alone through interstellar space would experience, with absolutely nothing to shield it. Methane would ordinarily be expected to break down chemically and disappear from an object's outer layers long before now, converted into other compounds by decades upon decades of unrelenting radiation exposure. Finding a strong, clear signal of it escaping the comet was a genuine surprise, one that pushed researchers to think carefully about where exactly it was actually coming from, rather than simply cataloging the detection and moving on. Scientists studying the data now believe the comet's outer layers had indeed lost much of their original methane over billions of years of radiation exposure, exactly as expected, and that what Webb detected was methane escaping from deeper, previously unprocessed material underneath the surface, material that had been shielded from that radiation the entire time and was only now being exposed as the comet's outer layers boiled away in the heat of our sun during its close pass. In effect, Webb was not simply examining the surface of this ancient visitor. It was reading chemistry that had remained locked away and completely untouched since long before our own solar system ever existed. Chemistry that had essentially been placed into deep cosmic storage for billions of years and only just now briefly become readable. Webb was far from the only instrument involved. NASA's Hubble Space Telescope observed 3IATLAS both shortly after its discovery and again after its closest approach to the Sun, providing scientists with their first estimates of the size of the comet's solid nucleus buried beneath all that glowing gas and dust. Because a comet's tiny solid core is almost always drowned out by the much brighter surrounding coma, researchers had to rely on careful modeling, combining brightness measurements at different wavelengths with assumptions about surface reflectivity to separate the faint core from everything glowing around it. Those estimates shifted somewhat as more data accumulated, starting with a fairly wide early range of possible sizes and narrowing considerably once the comet's activity settled down following its closest approach to the Sun, eventually settling on a nucleus roughly 2.5 kilometers across, noticeably larger than either of the two interstellar objects discovered before it, and part of the reason 3IATLAS became bright enough to study in such unprecedented detail in the first place. A larger nucleus simply means more surface area available to heat up and release gas, producing a brighter coma and a stronger, clearer chemical signal for instruments like Webb to lock onto. Size alone never guarantees good data, of course, but in this particular case, it gave researchers a genuine advantage over what they had to work with during the fainter, smaller encounters in 2017 and 2019. Additional instruments added still more pieces to the puzzle. A space telescope called Sphere-X, built to survey the entire sky in infrared light, observed the comet in December of 2025 and detected increasing activity following its closest pass by the Sun, along with dust made of tougher, more heat-resistant material, plus additional gas signatures. Ground-based radio telescopes using a technique called ALMA observations detected still other molecules escaping the comet, including methanol and hydrogen cyanide, adding further detail to its overall chemical story, while separate visible wavelength spectroscopy detected gas phase cyanogen and atomic nickel independently, confirming Webb's own findings. Given how extreme this object's trajectory turned out to be, and how surprisingly large and old it proved once studied closely, some corners of the internet inevitably speculated it might not be a natural object at all, offering various theories about artificial origins once word of its unusual size and age began circulating. Scientists took that curiosity seriously rather than dismissing it outright, treating it as a legitimate question worth actually checking, rather than simply waving away. Researchers used radio telescope arrays specifically designed to search for so-called technosignatures, meaning any artificial radio signal that might indicate an object was constructed, rather than formed naturally, the same general approach used for decades in the broader search for intelligent life elsewhere in the galaxy. Those instruments were pointed directly at 3IATLAS throughout its passage through our solar system, listening carefully across a wide range of frequencies for anything resembling a deliberate, structured signal. The result was unambiguous. No artificial signals were detected anywhere, at any frequency, during any portion of the observing campaign. Every single piece of data gathered, from Webb's chemical fingerprint to Hubble's imaging to the dedicated radio searches, matched exactly what a genuine ancient natural comet should look like. Chemistry unusual by our solar system standards, certainly, but entirely consistent with an icy body that simply formed somewhere else in the galaxy under different conditions than the ones that built our own solar system's comets. The actual, fully verified science here needed no embellishment to be remarkable. A confirmed visitor from another star system, possibly billions of years old, carrying chemical fingerprints frozen since before our own sun existed, studied directly by our most advanced space telescopes, already ranks among the most extraordinary natural discoveries of the decade without requiring any speculation to make it more interesting than it already was. It's worth pausing to appreciate just how much coordinated global effort went into fully understanding this single object in such a short window of time. The initial detection came from a ground-based survey network built primarily to protect Earth from hazardous asteroids, an enormous bonus catch entirely separate from that system's main purpose. Confirmation of the object's interstellar origin and precise orbit involved observatories and researchers across multiple continents comparing notes within days of the initial discovery. Space telescopes operated by different national space agencies then took turns studying the comet from orbit, each contributing a different piece of the overall chemical puzzle, while ground-based radio telescope arrays added still more detail from an entirely different part of the light spectrum. This kind of rapid, coordinated international response, teams around the world sharing data and coordinating observing schedules in real time, all working toward a single shared goal of understanding one ancient visitor as completely as possible before it disappeared from view for good, represents one of the more genuinely impressive examples of global scientific cooperation happening quietly in the background of everyday news coverage. What makes an object like this scientifically valuable extends well beyond any single comet story. Every interstellar visitor astronomers get the rare chance to study up close hands researchers a genuine physical sample of material that formed around a completely different star, something no amount of remote spectroscopy pointed at distant stars could ever provide directly. We have had exactly 3 such opportunities in all of recorded history, and 3IATLAS delivered by far the richest dataset of the 3, thanks to its size, its activity, and the sheer amount of advanced instrumentation now available compared to what existed when the first interstellar object appeared back in 2017. The fact that humanity has now confirmed 3 of these wandering visitors within less than a decade, with detection technology still steadily improving every year, suggests these objects may be considerably more common throughout the galaxy than scientists once assumed, quietly drifting past undetected, simply because earlier generations lacked the tools or the timing to catch them. For a long time, researchers genuinely debated whether interstellar visitors of this kind represented rare, once-in-a-generation events, or whether space is instead full of them, passing through undetected purely for lack of adequate instrumentation and observing coverage. 3 confirmed detections within less than 10 years, especially with each generation of survey telescope proving more capable than the last, tips that debate meaningfully toward the second possibility. That shift matters because newer, more powerful sky survey telescopes are already coming online, and scientists broadly expect the detection rate of interstellar objects to climb significantly in the years ahead. A brand new ground-based survey telescope, purpose-built to scan the entire visible sky every few nights with extraordinary sensitivity, recently began full operations, and many researchers expect it to dramatically shorten the gap between an interstellar object's arrival and its confirmation, giving astronomers even more advance warning than the months of lead time 3IATLAS provided. More warning time translates directly into richer science, allowing teams to schedule instruments like Webb and Hubble well ahead of an object's closest approach, rather than scrambling reactively the way researchers had to with the very first interstellar visitor back in 2017. In other words, 3IATLAS may not turn out to be some singular, once-in-a-lifetime event at all. It may simply be the third confirmed sighting in what eventually becomes a fairly regular stream of ancient wanderers passing quietly through our solar neighborhood, the vast majority of which we simply have not yet had the tools to notice. Consider the full arc of this particular object's story for a moment, because the scale of it is genuinely difficult to hold in your head all at once. It formed billions of years ago around a star that may no longer even exist, somewhere in a completely different region of the galaxy, condensing out of the same kind of disk of gas and dust that eventually builds planets, moons, and comets around any young star. At some point, a gravitational disturbance, perhaps a close encounter with a passing star, flung it out of that system entirely, sending it drifting alone through the emptiness between stars with nothing to orbit and nothing to warm it. For possibly billions of years afterward, it tumbled through that darkness, carrying its original chemistry, frozen and undisturbed the entire time, indifferent to whatever was happening back in the star system that had once been its home. Then, purely by chance, its long, silent path brought it close enough to our sun for our solar system's gravity to finally bend its trajectory and for our telescopes to finally notice it at all. It swept past the sun, warm just enough to release some of that ancient material into space, giving our instruments a brief window to read its story. And then continued on its way back out into the galaxy, most likely never to be seen again by anyone. Telescopes themselves have existed for only around 400 years of human history, and space telescopes capable of reading a comet's precise chemical fingerprint have existed for only a few decades. Out of the billions of years this object spent drifting silently through the galaxy, it happened to pass near our sun during the exact narrow sliver of human history when we possessed both the knowledge to recognize it as interstellar and the technology to study it in real time. A few centuries earlier, it would have simply been an unexplained smudge of light in the sky, gone before anyone understood what they had seen, its ancient chemistry never read, its story never told, just another quiet visitor passing through, unnoticed the way countless others likely have before it.